Alright, welcome back. So in this problem, we have a water tank that happens to be shaped like an inverted cone. So that's this picture here. So water sitting in our conical tank here. Our cone has a height of 6 meters and a radius at the top there of 1.5 meters. So what we're asked to do in this problem is saying if we have a full tank, how much work is required to pump the water to the level of the top and out? So we're just going to be pumping it right out. Pumping the water right out. How much work is required in doing that? That becomes our question. So we set about answering that. And to do it, what we're going to need to do, of course, is figure out how to do it for one little piece first. Right? So we cut a sliver out. Right, and we're doing it for this little sliver here. Right, that's our y sub I interval. Right, so we want to approximate. So to do that, we need to figure out, okay, what's the area of the cross section? And we very quickly realize that the cross section here, as we come across, is a circle. And we know that the area of a circle is just pi r squared. So the area for that subinterval there, we can say, is pi times the radius for that subinterval squared. Radius for that subinterval squared. But now, what's the radius? Well, to do the radius, we need to realize what's going on here. How was this cone originally generated? Well, a cone is generated by taking a straight line and revolving it about an axis, in this case, the y-axis. So what I can do is take my information here, the 6 meters, into 1.5 meters, and I can use that to draw a picture here of what's going on. If I set, for convenience, my origin at 0, 0, the tip of my cone to be at 0, 0, then it has a height of 6 and a radius of 1.5. So that means this line would come to this point right here, with a height of 6, and on the x-axis, 1.5. So we can figure out the equation of that line, because what we need to know is the radius at a given point. And that would just be this length here, or actually just the x-coordinate that corresponds to some height y sub I. So we need to figure out the equation of this line. Well, we know a point 0, 0. We also know we have the point 1.5, 6. So we can figure out the equation of that line. We can figure out the equation of that line. We have 1.00, second point there. So we can figure out the slope of the line, which would be the change in y, 6, over the change in x, 1.5. 6 over 1.5 would be 4. So this line has the equation y equals 4x. But now for my radius, I need to express x in terms of y, because we're going vertically. So we need to express x in terms of y. And that would actually be my radial length over here. So notice that in this problem, r sub I is just the y value divided by 4. Right? That's my x value, which is also my radius. So with that in mind now, then we know what a sub I is. A sub I is just pi times y over 4 quantity squared. And then we're going to lift a fluid completely out of the tank. So that's going from 0 to 6. And the height that we're lifting it is going to be 6 meters. That's where we have to lift everything, minus where it's currently at. Minus where it's currently at. So putting all this together, the work is going to be the integral from A to B of rho g times A of y times the height, which in this case is going to be 6 minus y dy. And we know that our area here for the cross section is just pi times r squared. Pi times r squared. So rho and g are constants. This is a water tank, so we're lifting water, so I'll bring in the density of water in a minute. Gravity is 9.8 meters per second. That's usually what we use. Okay. So rho g, actually it should not use AB anymore. That should be 0 to 6 of rho g. So my area function is just going to be pi times r squared. Current height y over 4 squared times 6 minus y dy. Right? And then we just go through and compute. So y squared over 4 is going to be y squared over, y over 4 squared is going to be y squared over 16. Right? And that's going to distribute. So here I'm going to factor out the rho, which is a constant, g, which is a constant, pi, which is a constant, and then roll 0 to 6, and then we multiply through. So that's going to be 6 over 16 y squared, and then that's also going to be y squared over 16 times the y, so minus 116 y cubed, and then times, or dy. All right, so now we're just ready to integrate. So add 1 to that, y cubed, become y to the third. So, of course, divide by 3. So what's going to happen when you simplify here? Rho g pi times, that's actually going to just become 1/8, because the 6 and the 16 first were reduced to be 3/8, but when you divide by the 1/3 for the y cubed, 3 cancels out. So we have 1/8 y cubed, and then here we'd add 1 to it, becomes y to the 4th, divide by it. So that would simplify to be 1/64 y to the 4th, and then we evaluate this between 0 and 6. And when you do that on a calculator, you will get 6.75 rho g pi. Now, if you're dealing with water, the density of water is 1,000 I think that's kilograms per cubic meter, if I recall correctly, and then times gravity, and of course times our pi. Right? And when you do that, you will find out that it will take 207,816.35 joules of work to empty that conical tank. Empty that conical tank. Now, second question is, what if our tank is only half full? Is only half full. Okay. Then the setup is still the same. We're still taking the cross section. It still has to be lifted at a height of 6 minus the current height. Meters. So everything else is all going to be the same. So if you were doing part B, which says What if we only have a half full tank? Rho G pi from 0 to 3 of all that stuff that we would have again, which would eventually just work out to be rho G pi times the integral of 1/8 y cubed minus 1/64 y to the 4th, which comes out to be 2.109 rho G pi, which we again could put all the numbers in and get it. But the important thing to notice is that's about less than a third of the total work, which really should make sense when you think about it, right? There's a whole lot more volume in the top half of that cone, even though it's being lifted a shorter distance, right? It makes sense that since there's so much more volume, and that of course would mean since there's more volume, there's more mass, which means there's going to be more force involved. Okay. So even though it isn't being lifted as much, there's still a lot more. So yeah, it makes sense that it necessarily wouldn't be half. It wouldn't be half of the actual work. And again, we could throw in our values 1009.8 pi, but here I'm just going to leave it in a rho G pi form. Again, we could get the actual value, but it's easy to compare that to that. Okay. So that's dealing with work of lifting a fluid from some container. Now, a reasonable question might be to ask, and this is one maybe you'll even run into it in the homework, is what if the thing we have is a cylinder? What if the thing we have is a cylinder? Will it take, half as much work to empty a half full cylinder as it would a full cylinder? Or is there something else still going on even there? That would be a reasonable question to ask. Right? If you have a half full cylinder, does it take half the work to empty that? Or is it still something else? So that's a question you could definitely ask yourself there. And you could work it out. You just have to come up with the cross section, which at least for a cylinder, actually will be a constant. It doesn't vary like the cone does here.